Hey everybody, Dr. A here, and in this video we're going to be providing a little bit of background information on torsional springs. So what does that mean? What do we think of when we think of a torsional spring? Well, let's discuss it. So when a connection has flexibility to rotate under an applied torque T, it can be thought of as what we call a torsional spring, and a form or a version of Hooke's law will govern its behavior. Now that's provided that it behaves linear elastically. So what do we remember about Hooke's law? Well, for a linear spring subject to axial force F, we have the relationship force equals a spring constant times an axial displacement, which I'll call delta. Now, if you remember from Physics 1, let's say you have a spring here, and you have the spring is at rest at first, okay? And then, let's say that you take that same spring and you apply a force and it stretches, okay? Let me draw this a little bit better for us. Okay, so there's that force F, and we have that stretched amount, all right? Now, the stretched amount is what we're calling this little delta, all right? And so what we built here in this relationship, or what Hooke built, was K is what we call a spring constant. And what it is it's a proportionality value or proportionality constant between the applied axial force F and the amount of stretch delta, okay? So the question becomes, how does this apply to torsion? Well, you can have a similar relationship, okay? So for a torsional spring, and I'm going to put spring in quotes because it's usually not a real spring. It's usually just an element of flexibility in a connection subject to torque T, all right? What we can have, for example, is, so we have a connection here, and let's say we see it very often in a connection with slotted bolt holes, okay? So these right here are like little slots, and let's say that we have a bolt here at one edge of each of these slots, okay? And then you apply this torque T, and so what will tend to happen is this connection or this plate with these slots here will tend to want to rotate. Now, where would the shaft be? Let me ask y'all a question. Where would the shaft be? Well, the shaft would be right here, kind of in the middle of this of these slots coming out at you. All right, let me draw this shaft a little bit better. So that's the cross section of the shaft coming out of the screen at you. So the plate that it's connected to will tend to rotate. Okay, and so what we can do is we can build a torsional version of Hooke's law by saying T is K times phi. Okay, now what is K here? K is a torsional stiffness. Okay, so K is a torsional stiffness. So what would the units of K be? Well, if you think about it, K is, again, it's a ratio of torque moment to an angle of twist, right? So if you rewrite this, you could say K is that constant of proportionality of T over phi, okay? And so what would that give us for the units of K? I'm going to use this triple equal sign, which means has units of. So it would be force times distance, okay? That's the units of torque, and then divided by radians, because phi has units of radians, okay? And so from here, we can use this model to incorporate or to model a flexibility of a connection due to an applied torque load. And that's going to contribute to or affect, per se, your angle of twist in the shaft itself, all right? So think about it. The shaft itself is going to experience an angle of twist, but since the collar or the connection is also rotating due to that flexibility, you're going to have an additional twisting from this phi value at the connection, okay? So that's our background on what we would call torsional springs. If you found this helpful, please hit like and subscribe, and we're going to see an example of us using this and applying this numerically in another video. Thanks for watching.